Hello everyone, I'm Anil Khanal. Nice to meet you all. And today here we are to talk about one of the possible sources of data in the near future using satellite constellations to observe the water level at different lakes and reservoirs around the world. And to give you a brief, just to give you a brief introduction about what is an altimeter, the satellite constellation we are talking about. Basically, it's kind of a radar that sends a pulse of radio frequency that is close to the frequency of radar, and when it strikes the reflective surfaces like water bodies, like sea or lakes or the rivers, then it gets back some signal, and from that we can measure the water level at different water bodies around the world. So to see how this technology that has been in development for quite some time, it's around 25 years since the altimetry has started in the satellite, but it was used mostly in the sea and ocean topography. But now, in the recent days, with the improvement of altimetry, it has been possible to use it in a smaller water bodies like river and lakes to see how we can exploit this technology going in the future and how it can be useful to solve the problems of water availability around the world. We have a panel of experts from around the world. We have Dr. Philippe Mazogrande from CNES, and who will give us a keynote. And we have Professor Eke Gosai from IIT Delhi, Professor Dr. Tania Grasosco from World Meteorological Organization, and Dr. Angelica Tapernelli from CNR in Italy, and we have Jerome Benevenis from ESA. Similarly, we have Dr. Silvia Bianca Maria from Lagos, and finally we have Dr. Cedric S. David from NASA. So let's start the discussion. Let's start the discussion with Dr. Philippe Mazogrande from CNES, the French Space Agency.
Yes.
Where this idea of using a small constellation of altimetric satellite to get a very high revisit of revisit monitoring of lakes and rivers around the world started together with the lab Lagos as a concept of SMAS. Let's hear what he has to say about this topic more.
Thanks a lot for this introduction. Well, my name is Philippe Maisongrande, and I'm going to give you this introductive talk on behalf of me, of course, and on behalf of Selma Cherchali, who's heading the Earth Observation Department where I work, and where I'm in charge of the land surface, some of the land surface programs. Selma is not able to give this talk today. This is why I'm replacing her. I'm going to do my best to introduce you some few consideration concerning the water cycle and the way satellites can be helpful in order to monitor this resource, water. So on the first slide, on the front slide, you can see these two scales are presented. On the right part, there is this usual picture of Earth with the relative amount of available water. The salty water is the blue sphere, while the two small spheres on the right of this are respectively the sweet water, and the very small one that you can probably almost not see is representing less than 1% of the total water on Earth, and this is the reachable water, the water that people can use, that people can extract from their environment. There is only a small amount of water, but it's not a question of water amount on the global scale. It's a question of where and when this water shows up, and from time to time you have too much water, while on the other hand it happens that you have drought then, and that you have lacks of water. If we had to summarize the main issues concerning the water management, the plot is the following one. Of course, water is at the very center of the SDGs, the Sustainable Development Goals. But if we want to summarize, we would say that we have three different very important points. The first one is that on Earth by 2050 will be 2 billion people 2 billion additional people on the planet, and this will increase the pressure on energy and the pressure on food. It will also increase the pressure on transboundary basins and increase the population in fluvial and coastal areas. The second important issue is the biodiversity, the pressure on the habitat, and especially in rivers, in wetlands, and in coastal areas. And of course, the management of these areas, for example, with dams, and for the connectivity, and it would have also an impact on the pollution, with an impact on health of populations. All these 2 points are of course stressed by the global warming effect, which is supposed to reach something like +2 Celsius by 2050. It will of course impact the water and the carbon cycle, and it will increase the number of floods. Sorry for the spelling mistakes. The number of floods, which represents something like 50% of the extreme events. It will also increase the number of storms. All these things means that we will require adaptation and mitigation takes involving science and application in economy, in ecology, in geopolitics, and in security. This is why there is a need for available, reliable metrics, which is homogeneous for a long time and on every scale, from the global scale to the regional scale. As a matter of fact, this one is not complete. As a matter of fact, there is a problem with information concerning water on the global scale. This information is not uniform. It's not uniformly distributed. It's heterogeneous. It's not accessible everywhere. The transboundary basins and the data sharing is not systematic on transboundary basins, and integrated water management of the water resources is not something obvious. And we all know that, for example, from GRDC. This GRDC representation, there is a collapse in the number of in situ measurements, for example, at virtual station at gauge levels. At the present time, less than 1% of water levels in a million of freshwater lakes are monitored, but it's not enough, and this number is not constant. This is why the Earth observation as a component, as a complementary information to the in situ observation. This is why the Earth observation is so important. We know for a while with altimetry, which has been introduced briefly by Anil before, we know that on the global scale, for example, with altimetry, we can monitor the sea level rise. The sea level rise, we've been monitoring that since the beginning of the 90s, and thanks to series of altimeters, it has been possible to make this monitoring of the average sea level rise, and of course we had to put a lot of efforts on the quality of the data that are involved in this kind of measurement, and it allows me to illustrate how important it is to have at our disposal homogeneous long time series, but also to have various types of observation at our disposal. All these recommendations, these requirements that show up on the right part of this overhead result from the requirements summarized by during the last seminar for scientific perspective at NES in France. And among the recommendation, of course, there is a strong one concerning accuracy, concerning resolution of satellite information, but also concerning the revisiting capacity. It's very important. This is why we address the point of revisiting capacity, especially illustrated by SMASH. The scientists' recommendation also highlight the advantages of the triangle between satellite information, in situ of information, and also models information. And in order to mobilize all this information in an integrated approach consisting in water, energy, or CO2 cycles monitoring, what we call today the digital twin Earth representation. Digital twin Earth is only an integrated approach. Integrating modeling has been considered by scientists for a very while. If we apply the same kind of measurement with altimetry, but instead of ocean, if we focus on the land, on continental surfaces, we can also have another kind of information on that example, extracted from the HydroWeb site, available on the thematic platform teyaland.fr. We have here an example of more than 20 years of Lac Nasser level monitoring. And this is another way to illustrate that even with the same space infrastructure, which means the constellation of altimeter satellites, you can afford a long time series like that, which is addressing the water level in a lake, which shows us that the same monitoring system makes possible the monitoring of the monitoring on the regional scale, which is the scale of management, which is the scale of decision making, and which is also the scale of validation. Validation making possible the high quality of time series, without which you cannot rely on this on your data. This was the example of altimetry, but altimetry is not the only way to monitor the water cycle. We have represented on this slide the water equation budget, the total equation storage on the left part of the equation, and the components, the inputs and the outputs of the water budget. If you consider the inputs and the outs, which means the right part of the equation, you have precipitate transpiration by vegetation plus the runoff. While on the other hand, you have the changes. You have changes of the total water storage, and you can see that all the components of this water budget equation, they take advantage of specific satellite observation programs, among which CNES is very often one of the principal space agency. For example, during the next we have you have SWOT for the runoff, and we also have Trishna. I will say some few words about Trishna later on. You also have Trishna concerning the evapotranspiration, and of course the AOS, the NASA CNES future mission AOS for precipitation. Of course, this slide concerns the water budget, the water amount, but we should not forget that satellite can be also very helpful in order to consider the water quality, the monitoring of the water quality. Water quantity and water quality are two aspects of the water issue that can be reached with satellites. The revolution is between well, it is stressed on the title of this overhead, but the main evolution in space mission for water concern, for example, the increase of the accessibility of data. Data are more and more available and with free access. This is true for the Copernicus mission, Sentinel-1, 2, 3, and so on. This is true for SMAP and for all the American satellite programs like Landsat. Second point, there is also an increase in accuracy. We go from, for example, concerning soil moisture, we've moved from AMSR E in C-band toward SMOS in L-band, which is more accurate to monitor the soil moisture. Another example for the vegetation water stress, we have moved from Landsat thermal infrared at 90 meters resolution, something like every 20 days. We have moved from Landsat to Trishna, increasing the revisiting capacity, going up to a 3-day revisiting capacity. Another improvement in the monitoring of water cycle by satellites is the increase in resolution, since we've moved from JSON to SWOT. JSON being displaying data at kilometric scale, while SWOT is able to monitor water at 100-meter resolution, of course, at every 21 days, which makes very important complementary monitoring with high temporal sampling, which is still needed, and which could be brought by SMASH. at least we have an increase in temporal resolution from SPOT 4. All the high resolution optical imagery they were initially available at let's say at the monthly time step, while today we have sentinel images every 5 days. This is a slide just to show you the last success of CNES and NASA. Of course, the SWOT mission was launched last December, and this overhead illustrates the swath of SWOT. This example is on the Congo River, sorry, on the Senegal River, and you can see the tremendous increase in the space coverage with thanks to SWOT every 21 days. And once again, this should be completed by small altimetry satellites for hydrology, which means SMATCH, and it's one day revisit at Nadir. The upper right picture shows you that, of course, with SWOT, you have a range of revisiting capacity. The further you go to north, the more often you can get a SWOT image. And since we talk about SWOT images, if we go toward the next slide, you will see one of the first SWOT images. Please, Anil, if you can. Okay, this is an example of one of the first SWOT images near Toulouse, and on which you can see the ability of SWOT to monitor and discriminate what I would call water objects, principally rivers, but also reservoirs in the area. And you can touch one of your keyboards. Thank you. And of course, the only drawback of this image with SWOT is the revisiting capacity will only be 21 days. And of course, with this revisiting capacity, of course, we have the image, but we won't have the sufficient time frequency in order to catch the high frequency hydrologic events as illustrated on this plot, the same area. Here I represent the two principal missions that either have just been launched, like SWOT, concerning blue water, what I call blue water, the running of water, and concerning also Trishna, which is dealing with the blue and the green water. These two missions, as I've said, will contribute to the water equation budget, but also to the monitoring of the water quality. Concerning Trishna, it's a thermal infrared imager, which will be devoted to the water stress monitoring. It will make possible the calculation of evapotranspiration, but it will also make possible the monitoring of water bodies, hydraulic geographic patterns and time patterns. These two information will be gathered in a database, which is named a data hub devoted to hydrology, which is named HydroNext. And Anil, if you touch the keyboard, the HydroWeb will show up. HydroWeb Next is a hub where will be gathered all this kind of information. First of all, the information that I've shown you before, the one of HydroWeb, the previous HydroWeb, concerning only altimetry, but you will also have information with SWOT, with Trishna, and many other missions that I will mention later on. Among a strong investment of CNES and its international partners on the Earth observation for water consists in a strong effort for mission satellites, plus a strong effort in the data monitoring. Satellite-wise, of course, we have all this bunch of monitoring missions. So SMOS for soil moisture, the JSON concerning classical altimeters, Megatropic, for example, for precipitation. We have SWOT for global water elevation, as illustrated before. Krishna, I've already mentioned that. We also have high resolution information at 1 meter resolution, allowing the mapping of digital elevation models. We also have satellites for precipitation and clouds, AOS and NCL, and of course, phase A dedicated to SMASH has just been carried on at CNES, and we really hope that we will find a programmatic frame in order to find a financial envelope to pay that. And to finish, I would like to put the emphasis on our needs. There is a need for a well-sized ground infrastructure. There is also a need for clear data policies and and intellectual property according to the level of products. Of course, you won't deal with the level 2 products the same way as you deal with level 3 or level 3 plus products. And this is also why we need a fair positioning of research in the considered public-private partnership.
I would like to add something to what Philippe Maisongrand just said about the EO missions. CNES is a very important partner in the European Space Agency and contributing to the future of altimetry in particular, and more like the launch of Sentinel-3 version C, version D, the launch of Sentinel-6 version B, and preparing the Sentinel next generation topography, and the other one like Sentinel-3 topography, which will have an altimeter and maybe an interferometric altimeter, hopefully. And the Crystal mission as well, which is designed for the ice, and but will work all throughout the planet. And all these are efforts that all the member states, space agencies are putting into ESA, and the CNES is one of the major partners, member state of ESA.
Sure, thank you, Jerome, for giving a complete dramatic landscape. Of course, I've chosen a French angle to illustrate the contribution of space, but of course there is the complementarity with ESA.
Sure. Yeah.
Yeah. Thank you, Philippe, and thank you, Jerome, for your insights, and thank you, Philippe, especially for giving us a map of where we were and where we come to this story into. Like, so first thing first, there is a scarcity of water globally, and it's expected that at the moment, World Bank projects around 30 to 40% of the people live in the areas of water stress, and the global population is estimated to grow up to 10 billion people from 8 billion at the moment by 2050, and there is going to be a 15% increase in water demand. In order to fit this demand into the supply, we need to increase our capability to monitor so that we can have an integrated water resource management, which takes these things into account together with climate change. To get more into what kind of things are measured, monitored, we will now hear from Dr. Angelica Tapernelli. She's a researcher at IRPI CNR in Italy, and she specializes in remote sensing, hydrological modeling, climate change, and hydrological risk assessment. Let's hear more from Dr. Tapernelli.
So thank you. Yeah, I am quite pragmatic on this discussion. So I focus on 6 main hydrological applications and how we can see this new constellation in our topics. So first, I would like to stress that for flood forecasting activities and hydraulic risk mitigation, we need accurate and timely water levels, a low latency for real-time use, and a sub-daily resolution. So this is an example that we did in the Niger basin, specifically in the Benue River, in which we had the in situ discharge at Makurdi station, and we use altimetry upstream the river reach to estimate the discharge downstream, and in a forecast of 4 days ahead. Indeed, we reconstruct the rating curve between the water surface elevation altimeter at a certain time t, and we link this water surface elevation with the discharge at time t plus the wave travel time, and we use this information to alert the population during this flood event. So in this case, of course, this was synthetic, so it means that with a new constellation, it could be very useful to have a timely data, and in the way that we can use this data in real time for this kind of application. The second topic is the climate change. So for identifying and adapting the potential effects of climate change, we need long-term water level estimates at monthly scale. That it doesn't mean monthly resolution. Here, another example in which we used basically the altimeters to extend the temporal series of ground stations. So we focus on 70 sites across South America, Africa, and Asia. And we use the blue, as you can see in the right blocks, the blue time series recorded at the ground stations. And we extend this blue time series of river discharge in this case with the red one that are the river discharge coming from the altimeters. And extending this temporal series, we were able to reproduce to estimate the climate trend over all the sites. In this case, a new constellation can guarantee continuity in the long-term monitoring. Another application is for water resource management. And, we need, in this case, a high spatial coverage and at least a weekly temporal resolution to monitor also small reservoirs. As an example, I extract the 6 biggest lakes in Italy, 4 in the North Italy and 2 in the center. And what you can see if we consider the emissions that are currently on the sky now, not what in this case, so the JSON also in the past because there is MBSAT, but MBSAT can be replaced with Artic and so on. So Sentinel-3A and B, we can observe that there are a lot of wall between the tracks, and this means that we cannot estimate, we cannot have a monitor of these big lakes. So let's imagine for the small reservoir, and we know that for small reservoirs, the monitoring of this small target is very useful also for ecological application. So if well planned, the new constellation could increase the number of virtual stations, and it will be very useful for hydrological and hydraulic. In terms of engaged rivers, of course, we need multi-mission approaches and daily temporal resolution. In this case, I want to show you this example. From two papers, I selected these 2 figures. On the left, there is the in-situ data over the Africa, and on the right, what we can observe with the altimeters. So we have a significant increasing in the number of the measuring stations. But of course, all these points are at least a temporal frequency of 10 days. So it means that if we consider, for example, Sentinel-3, in the orange there is a flood event from Amazon River, and we are quite sure to catch almost all the dynamic of the floods. But in red, you can see the Po River, and in this case, we miss almost all the dynamic of the river. So the multi-mission approach is very useful because, as you can see on the right, we can have a very detailed information, at least not daily so far, but we reach every 3 days of resolution. So the new satellite constellation alone can cover the increased revisit time. And of course, it can be still used in multi-mission approach to increase again. For hydrodynamic modeling, we need daily resolution for parameter calibration. And here I selected 2 examples. On the left, there is the use of several missions for the calibration of manning parameter of an hydraulic model over the Po River. And on the right, the same models, but we use a different satellite that is Cryosat-2 that has an intertrack over the Po of 7 kilometers and almost 1 year of temporal resolution. And what we can see here is that we are able to reproduce very well the change in the manning along the river, and so we can improve this information just because the station is able to improve the spatial information. So for the hydrodynamic model, the constellation can give us an important contribution, of course, and if we can guarantee the daily resolution, it can be used also for hydrologic hydrological model calibration, not only assimilation, that is what is quite used to now. Finally, for monitoring extreme events, flood and drought, we need daily resolution for medium-large basins. I extracted this temporal series from the IT platform, and you can see the reproduction of the water level for the Po River normal condition. There are some flood conditions, so some flood events, and there is also the big drought that occurred last year in the Po. So actually, the more temporally dense information, the greater the chance of observing extreme events. In this case, the constellation can be very useful if it is well planned, and of course, it depends on the size of the river, but we have a great potential.
Thank you, Dr. Tarpanelli. It was interesting to see from Philip's presentation to yours, from seeing what is coming and like what is the state of art in the space domain for hydrology to what is actually needed in the ground with different use cases. And some of the things that you mentioned and that are like you saw different use cases like for climate change, for water resource management, modeling, calibrating models, and to do some kind of prediction of extremes like droughts and floods. So this was very interesting. And some things that I really noticed was you talked about the scale, about the necessary scales for different types of uses, spatial scale and temporal scale. So this was quite interesting to hear. And one of the things that you mentioned was virtual station, a concept of virtual station. So basically, to our viewers, what is a virtual station is basically, you can imagine that a satellite is going along a track and it projects beams in a certain area in the earth, and along this beam path that is projected on the earth, whenever we have a water body that crosses this beam path, we call it intertrack. When the water body crosses the intertrack, we call it a virtual station. Just for this clarification, thank you very much for everyone. We will have a discussion session with our panelists in the end. If you have your questions, please write it in the Q&A session, and you will be able to hear what panelists think about your questions and how do they answer it. Thank you, Angelica. We will move on to our next presenter, who is Dr. Cedric S. David from NASA, JPL Lab in NASA. So to tell something about David, he was a principal investigator in the hydrology part of SWOT altimetry mission, and he can give us interesting insights about what is the cutting edge in terms of application of altimeter in inland hydrology. And he's also actively running the global hydrological modeling and river flow within the large networks in the big basins with a project called RAPID. More from you, please, Cedric.
Thanks so much for having me. It's great to see such a large audience. I'm excited to be here to talk to you about observing river dynamics from space, and particularly why you might want to do that. I'd like to start with this little animation on the top here, which is the Congo River Basin in Western Africa. This is a one-year simulation at the daily time step, and what it shows you is that there is an incredible amount of dynamics even at the daily scale, which is an indication that, you know, if we'd like to observe exactly what's going on, daily observations could be helpful. Of course, everything starts with the blue marble. This is a picture from over 50 years ago, last time that humans set foot on the moon. The Earth is blue, that's why we have so much life, right? It's all this water, all the blue is water, but all the white is actually water here, whether it be clouds or the ice caps. And in this picture, actually, it's the first time that we ever saw the Antarctic ice caps from space. We've seen this picture before. So Philippe, I'm going to try not to repeat what you said, but so in the 100% of water that we have on Earth, 97% of it is salty, about 1.5% is frozen and fresh, another 1.5% is fresh but liquid. Now, so that's all water on Earth. The liquid water is there. The vast majority of that, 99% of the 1.5% is groundwater. I like to think of this in multiple terms. We've seen the oceans rising. We've seen the ice caps disappearing from gravity missions and from altimetry of ice. We've seen the groundwater is depleting from gravimetry measurements. And I think of groundwater as the savings account of fresh water, perhaps even the family heirloom, because groundwaters they take hundreds of years to replenish, and so it's a precious resource that is passed down from generation to the next. And that leaves us with surface water, which is the topic of our conversation today. I really think of this as the renewable component of fresh water, so more like the checking account. You don't go to the grocery store with your savings account or your retirement account. For everyday management, it's a good idea to start thinking about this renewable component of fresh water. I'm going to skip this slide because we've seen it. I will just highlight that the technology that we're using from space that Anil mentioned earlier today is basically the same that we're using from bridges with bridge-mounted radars, except that we're now flying those from space. We've talked about transboundary rivers. These are all the transboundary river basins in the world. The bottom line here is that everyone needs water, regardless of whether you're upstream or downstream. And if you're upstream, you're lucky because you get first dibs, but it doesn't mean that you are entitled to use all the water you have, because other people further downstream might have an important use for the shared resource. This is a map of global world population, human population, going back 10,000 years ago, or 12,000 years ago to now. About 200 years ago, it was only 1 billion with a B, humans on this planet. We're now beyond 8 billion. And one thing is for sure is that all of us need access to fresh water. The United Nations actually declared in 2010 that safe access to clean fresh water for drinking and for sanitation was a human right. So if we'd like to guarantee this human right for the 8+ billion and apparently soon to be 10 billion people on this planet, we have to start better understanding our fresh waters. Now, the water in rivers and lakes around the world is known to be not only the most accessible, and this is where human civilization started by Great River Valleys, but it's also the most renewable. And so it's known to have a tiny storage. It's about 2,000 cubic kilometers total in Earth's rivers, but it's mighty in flow. And so the tiny storage is critical because not a lot of water is a problem for water management. And the mighty discharge or the mighty flow is a problem because of flooding processing. And of course, we're sharing the water with the rest of the ecosystems on Earth. And so, we have to manage it for us, but also for the rest of the world. Now, our understanding of water quantity in Earth's rivers actually hasn't evolved that much since the 1970s. And what we've known is long-term averages of total amount of water in rivers and lakes and how much water discharges to the ocean. The numbers actually haven't changed very much since those reports from 1974. It was a Russian report from 1974 that was translated in 78. And it's about time that we start understanding not only the long-term means, but the dynamics of surface waters. And the dynamics, you can see that as simple as thinking about measuring the magnitude and the duration of events. So that's when you're looking at a given place and thinking through time. But you also need to understand how water moves from upstream to downstream. And for that, you need to think about propagation time or propagation speed, and also the length of these spatial scales of propagation. Now, if we allow ourselves to dream with a potential constellation of 10 nadir altimeters on a 10-day orbit, allowing for daily observations, you might be able to sample in an idealized manner in this particular study that was NASA funded but produced jointly with colleagues at CNES and at Lagos, who are named on top, one of which we'll hear about later. Hi, Sylvain. It's great to know that you're here. So we did a simulation of the Congo Basin, the same simulation that I showed earlier, and then we ideally sampled all these measurements. So what it tells you is we're seeing a whole lot of dynamics at a handful of locations. And that brings me to my near final slide here, which this potential concept, I really see this as an ally to the SWAT mission that was launched in December last year that we already discussed today. On the left side here is SWAT, which is very fine in space, but relatively coarse in time. The 21-day revisit is nice to see the area. But it's because of overlaps in the swath, we'll get more than every 21 days, maybe every 10 days or so on an average around the planet. But we'll see everywhere, and that's pretty great, a very fine resolution. If we were to be able to put together this constellation of 10 satellites, we'll see less in space, but so much finer in time. And if you're able to do the math and put that together with some simulations of river systems around the world, I think we might be able to reach the spatial-temporally seamless transport of water within Earth's arteries that you see here at the center. And I think that will not only be the key to enabling water management, but also to prevent water-related disasters. And I'll stop here. Thanks so much for your attention.
Thank you, Dr. Cedric. It was very interesting indeed to see what has been achieved in terms of observing lakes and rivers from space, because as we know, in the last 25 years of history of altimetry, most of it had been dedicated to observing oceans and seas. And it is very interesting that now we are able to observe very fine resolution images of water bodies in the earth. Hence, we have the capabilities to observe the lakes and rivers, which, as you said, is the taking account of our water balance, the one that we have to observe daily. And just to say that the global climate, the water levels in lakes and rivers are considered one of the essential climate variables in terms of building climate resilience. And it is the breakthrough observation point is recommended by GCOS, Global Climate Change Monitoring Observations System, is actually 1 day of revisit of river discharges and water levels, and up to 30 days of lakes. This is what is recommended to achieve a significant improvement over what we have. And ideal would be to have 1 hour observation of river discharges and water levels on the river. Thank you very much. Again, once again, if you have questions to Dr. Cedric, please don't hesitate to send it in Q&A. We will discuss it towards the end. To move on with this philosophy of one small step for man and a large leap for mankind, similarly to see what kind of revolution this altimetry can bring, and what is daily revisit can bring, and what is the status of water resource monitoring and water resource management in ungauged basins and global south. We have Dr. A.K. Gosai from Indian Institute of Technology. He is a seasoned professor and expert in water resource management in the region. Please, Dr. Gosai, you have the floor.
Thank you. Thank you. It was nice listening to all the previous speakers. I think it's a very important issue which we are discussing. No, I have not, I must admit that I have not been using the altimetric, the products. Though I'm a modeler, what we have done is we have done the simulation using the hydrological models of our basins. And we also have early warning systems created where we are using the rainfall forecast of India Meteorological Department and giving the flow forecast at different locations of the basin. I think in this particular discussion, I'll try to be projecting myself as a user, that what I like to see in these products, where they can help in making our water resource management more meaningful, and helping the managers in doing their job in a better manner. I feel that there's no doubt that additional observational points in a basin will give us a lot of confidence in terms of how the variability of this very precious resource is happening in actual practice, not spatially, but also temporally. And we are talking in terms of very huge basins. When we talk of India, we look at the basins of the size of Ganges, which is 1 million plus square kilometers. Similarly, the Brahmaputra basin. And all our basins are big basins. Most of them are multi-state basins. They're equivalent to transboundary basins of other countries. What I feel is that the most difficult part when we are doing the modeling and we are trying to use the models for various water balance assessments, the most we miss is wherever there are man-made interventions. You have reservoirs. You don't have any observations on the reservoirs. They, even if they are there, they are available locally at the state level and they don't become available in a public domain. So if we have these options available where we can indirectly look at how the water level in a reservoir is changing or any other water bodies is changing, we'll have a lot of additional information, and we can also try to understand how the release is taking place, because that is the data which is normally not available when we are trying to validate your models. So the release for various purposes, whether it's irrigation or whether it's for the domestic utilization or industrial utilization, that data can become available through this mechanism. Secondly, I also, the more I think, if we have on a daily basis how the water level is changing in a water body, it will also give you the spread area of water. So it will bring in another dimension in terms of knowing that what is the volume which is being stored in these water bodies, what is the shape of the reservoir. Because most of our reservoirs, they don't remain full all the time. They are seasonal reservoirs. They get emptied by the end of them, by the beginning of the next monsoon season. So you can also get out of this a very important additional information that how the reservoirs are getting silted up, what is their volume, what is their area capacity relationship, which is very useful for any of these assessments which you normally need to be making. So that will be another additional benefit which will be coming out. And as Angelica was also mentioning, that you can use this for the hydrodynamic modeling, that how the water surface profiles are changing. Since you are going to have the water surface profile data, and there also you can also derive out of this information the cross sections of the rivers, because you are having during the monsoon the maximum cross section, which is wetted with the water, with the high level of water flowing through that. As the season becomes closer to the non-perennial season or the non-monsoon season, your more and more area will be exposed and the width of the river will become smaller. And this information can also give you a good indication about the cross section of the during the non-monsoon period. Some of the non-perennial segments of the river might become totally devoid of water. So you will even go to the bottom of the river at that cross section. So I'm really very bullish that if we start using these outcomes of the altimetry and even going to the next level of nano satellites, where we are expecting to have even a daily level information and also more coverage in terms of the spatial resolution, I feel that this is going to be a game changer, and we can improve our assessment of water resources, as well as we can validate some of the predictions which are being made in terms of various components of the water balance, and help the water managers in really coming out with a better understanding of their basin and also incorporating the dynamism of the basin. So I think that is something going to be a very important in future, and very soon we'll like to be using some of these products and making our existing the applications which we have made. I'm going to share with you the link which we have for the portal where we are simulating all the basins of the country on a daily basis. And those people who are interested, they can have a look at that, and I think will be and also give us some feedback. So I'll stop here and maybe respond to any questions if anybody has. Thank you.
Thank you, Professor Gosai. It was very insightful to see what is actually needed, especially in Global South, where we know that hydrological measurement networks are quite weak. And as you mentioned, we have to depend mostly on the hydrological models that are driven from the rainfall in order to observe these surface water fluxes. And you gave us different parts of it. So to make it flow the conversation, I would like to ask Dr. Silvia Bianca Maria to join us in order to see, what does a constellation of something that was imagined as mass at the Lagos lab would bring to address all these questions that were raised by Dr. Gosai and the previous speakers. So basically, Dr. Silvia Bianca Maria is from the Lagos lab in Toulouse, France, and this lab is one of the principal investigators of these early stages of satellite constellation, which was also known as MASS, and we would like to hear more from him.
So thank you for this opportunity, and thank you for all the previous presentations, which are very interesting to see what is needed. So sum up, SMASH came up a few years ago thanks to Denis Blumstein, who unfortunately retired last year, and also with Stéphane Calment, and a discussion with other hydrologists here in Lagos. So they got to this idea that we need now to have a better time sampling from altimetry. So with SWOT, as it was said by Philippe and also by Cédric, we can now have access to the global. We can now have access to a global observation, spatial global observation, thanks to SWOT. However, we still have an issue with the time sampling. The best time sampling we can have from Nadia altimetry right now is 10 days from Sentinel-6. And the purpose of SMASH is really to assess or to leverage this issue. So I also wanted to highlight that SMASH and all the remote data are of course not a replacement of in-situ gauge network. They are complementary, and of course, if we can have in-situ measurements everywhere we want on Earth, it will be better. But right now it's not possible. So in-situ can be used where we have the data. Of course, where we don't have in-situ measurements, a satellite can be to provide complementary information. Especially Nadia altimetry has actually three main issues. It's the vertical accuracy, which is measuring the water elevation, which is not the water depth. The root mean square difference that we can have with in-situ measurements that are not always and most of the time not under the track of the altimeter is at best 20 centimeter over rivers. The other issue, as mentioned previously, the space resolution, because Nadia altimeter are only giving measurements along the satellite track. So SWOT and maybe the next generation of Sentinel-3 might address this issue. The other is the time sampling. And for that, we have nothing, and we know that for operational or even many scientific applications, this is an issue. So that's why Denis, Stéphane, myself, and many others were proposing a SMASH. The idea of below SMASH is also to provide an altimeter that is designed to observe rivers, which was not the case for almost all the other previous altimeters. We were conceived to observe the ocean first and used as opportunity over the land surfaces. So we think SMASH can be very useful to observe the river that are around 100 meter, even 50 meter if we are lucky, river width. And it can be also useful to observe some floodings that have their time scale that are compatible with daily sampling, which is not a daily average, it's just a daily sampling, so every 24 hours. So it's not all the floodings, obviously, but it's much more that could be observed with MASH than what has been observed by previous satellite mission. To get daily observation, of course, just one satellite cannot do that. So that's why the idea is to conceive the 10 satellites, and the SMASH concept relies on those needs. I don't have any slide to share or to present, but of course, should keep in mind that this daily sampling is also important to observe the rivers that have the dynamics that are compatible with those type of sampling, which will still be very very interesting to complement what can be done right now. You mentioned climate change. I agree, but we need, of course, to have a lot of years. So we need to have a long time series to do that. So the SMASH constellation should work for many years to be useful for climate. And if we now have a good archive of altimetry data, but it's also very useful to observe the dynamic of rivers that we can that is currently under stress due to climate change, but also due to direct human infrastructure. So even for the first year, and I guess for stakeholders, and studying how the human influence the water cycle, SMASH could be very beneficial. I think I've spent my time slot. So if you have any question, I will be, of course, very happy to answer. And also, I wanted to highlight, and I think a few other people have already said that. I really think that we need to have this type of data that could be delivered freely, especially for stakeholder, low-income countries, and but also for science with different data latency, of course. So thank you very much.
Thank you, Dr. Bianca Maria. It was very interesting to hear about actual idea of how this mass comes into action, what it can do, what does a satellite constellation that we talked about of 10 nanosatellites in a 10-day track can and cannot achieve. It was a kind of reality check as well, because not everything that we think is coming up is always solving all our problems. And as you said, it would be complementary to the missions that already exist, and it will be complementary to the ground stations that already exist, because without in situ validation, in the end, we will still have a big uncertainty of what we see, if it's the reality or not. Thank you for this. To move on a bit quickly, because we are running a bit short on time, I would like to ask Dr. Jerome Benveniste from ESA to talk mostly about his experience, because he originally started a long time ago in altimetry in the oceans and seas when it was a trend, and he has been using altimetry for for inland hydrology, and we would like to see like what is his experience and how it has evolved in 25 years and where we stand now, and how does this kind of the technology brings promises to ongoing basins. And he worked quite some bit in Africa. So Dr. Benveniste, please, the floor is yours.
Thank you very much. So I just want to thank Philippe, Angelica, and Sylvain, and Cedric, and so on, having introduced very well the panorama of hydrology from space, also mentioning what is needed and what is not needed. I mean, I'm not sure nothing is not needed, but the requirements that we have in order to have a better management of water, and especially to cope with extreme events, be it lack of water or excess of water. So I'm going to tell you a few things that we do at ESA. And on the next slide, I show what is our objective. If you can go to the next slide. So basically, we're contributing to pushing the frontier of science by doing everything we can, like engaging the community. I'll tell you a few words about that. And developing algorithm and product. I started River and Lakes 25 years ago, extracting water level from altimetry. And so on. We have, of course, concern on capacity building. And the last is a transfer to future mission. Next slide will just show you that we are organized in different missions. Like we'd like to launch big research activities. We do that as much as possible in good coordination with the European Commission, especially the Research Technological Development Directorate. We have established a certain number of clusters. We host scientists and postdocs at the Science Hub in Esvin, in Rome, Italy. And we're trying to push all the kind of observations to advance the understanding of the Earth system and develop, contribute to the development of a digital twin. And next slide will show you that we are dispatched in different clusters. And click again. We are. I'm really concerned by the polar and ocean cluster, but we're launching this new cluster called the ESA Water Cycle Cluster. Next slide. Consulting the scientists. I mean, what we call users on our side, be it scientists, people who are doing campaigns and matching the data, and also modelers. And we like to gather in workshops every 2 years or so. And this is the very important part. I mean, all the satellite missions need to have all the scientists be behind it in order to become one day operational. And even when it becomes operational, the scientists are very needed to make sure that what we're distributing to the users are of the highest quality possible. On the next slide, you will see that we are reiterating with this hydrospace in 2023. So I invite everybody to come to Lisbon in November, and last week of November. And this is important. We produce a report which is essentially a requirement and recommendation to the Space Agency. On the next slides, you will see that there is a certain number of actors. Traditionally, these are the ones of Hydrospace 2021 and so on. And it's very, very important that we all work together, be it scientists and managers, and eventually also stakeholders, in a sense, funding agencies as well. On the next slide, I'll show you what we are concerned about, and I won't go into the details because it's been said, but if you zoom a little bit by clicking the next slide button, you will see that the part where we have the rivers, the lakes, and so on, it's illustrated here as something very complex, and we have to do a major effort in order to have a good observation of this part. On the next slide, you will see that there is an important component of inland water hydrology. It's the interaction with the coastal ocean. Most of the people are building their homes and dwelling near the rivers, which makes sense because water is essential to life, but also near the ocean, in the coastal ocean. And here we have water from the hinterland and water from the ocean, which interacted. So if you click again, you will zoom on this coastal ocean and land sea interaction, which is something I'm trying to push as much as possible by launching research contract, organizing session here at EGU in Vienna, where I am now, about the inland water and the coastal ocean. On the next slide, you will see that we are now launching this new cluster on water, and this is an important aspect at ESA. We've been investing on the subject, and quickly on the next slide, we also have a multi-hazard cluster where we look at hydroclimatic extremes and floods, which are the words that are highlighted on the slide. And so on the next slide, I'll show you how we invest. We have the idea that we're going to produce, thanks to the past experience that was developed, especially in Perugia at IRPI, where Angelica works, the first space-based only runoff assessment. And on the next slide, there is the next type of investment that we do, which is the idea that we would put together all the altimetry together, the SAR-in, the synthetic aperture radar, the SWOT, and so on to compute river discharge. On the next slide, you will see that we're investing also in the interface between the hinterland and the coastal water. And there's a big contract ongoing right now called Hydro for the hinterland part and coastal for the ocean part. And this will have a follow-on. On the next slide, you'll see that we are also looking at coastal hazards, and coastal hazards is like something coming from the sea, like storm surge, but also coming from the land when we get inundation coming from the hinterland, especially in estuaries and deltas. Next slide. I've been, the next slide is, yes, the idea is to look at the observation and knowledge gaps that we have here. And flood forecasting surely needs to be improved at short scales, and at short and small scales, short in time, small in space. I've been involved in trying to do something and to give a helping hand for the United Nations mission in South Sudan. There's a refugee camp in Bentiu in South Sudan where there's 100,000 people displaced due to flooding. And they have both the UNMISS and the World Food Program and Médecins Sans Frontières have a requirement, which is a daily forecast with a few days lead time, so they know if they have to put a few more bricks on the dikes to protect the 100,000 people that have been displaced in this camp. And then right now, global models, which are fed with river level every 10 or 27 days, cannot really provide an accurate forecast. And so this is really something that we would like to push forward. And on the next slide, we have an idea of what's going on here. Like almost half of the country is flooded regularly, recurrently, and it has also an evolution between 1 year ago, 1 month ago, and what is now, which is the report that was published in October 2022, where there is a lot of variation. And you can see in white is flooded for longer than 50 days. That's the big problem, but there's also looking at flooded for the last 10 days and so on. And the idea is to be able to have good knowledge of river discharge, and let's say the whole water flow in catchment coming from Lake Victoria, and be able to do this forecast every day, and with the idea that they only need 3 or 4 days to know that the water is going to be rising or lowering. And so that concludes my talk by saying that we really need something that can provide data at much faster space than 10 days or 27 days. And the next thing is, I think we should also publish a little bit more what SMASH is capable of doing. I remind you that with Envisat on specular water, we were processing the normal classical altimetry in delayed Doppler mode because we had some coherence, and it would be nice to look at things like that. And I'm also very glad to see who is in the audience, and I think we can go far with this concept of SMASH. Thank you very much.
Thank you, Dr. Benveniste. It was an interesting insight on what using altimetry for rivers, and also you mentioned the coastal area, which we can imagine, as you mentioned in our previous meeting once, that it's basically a river with one bank, the coastal area. So it's very interesting that it's not just limited to the rivers with two banks. And also thank you for letting us know what is coming up with ESA, the European Space Agency, and like how you are trying to bring together different available resources to manage the knowledge and data gap we have. So we will take questions in the Q&A, please. And I would like to continue this discussion. Like the moment you said, like we are trying to bring different data sources, we have to talk about data, because satellite observation brings a lot of data, and now we are talking about the data of water that has been shared, that has been flowing through different countries. So different countries are stakeholder of this. So it's a very complex problem to solve. We also need to see in this side. So in order to see what kind of things can be considered, I would like to invite Dr. Tania Gascon from World Meteorological Organization to share her insights on sharing and building capabilities of sharing hydrological data between different countries internationally.
Hello, everyone. Good afternoon. Thank you very much for this opportunity. So, but it's now I can start talking about the questions that the subject that was suggested to address during this panel discussion. So basically, Anil suggests me to address the biggest challenge in water resources monitoring in Africa and in Latin American countries. So in regions like in Africa and also Latin American countries, so for instance, I'm going to talk about one example, one country that we are supporting. In Togo, so the measure of groundwater level from automated stations are limited to a few points in few critical basins. So and this information is not continuously available. So because there are problems with the equipment, problems with battery, vandalism, etc. So this condition limits the continuous monitoring of a specific variable, water level, but also it limits the monitoring that is doing through modeling. For instance, in West Africa, there is a system called FANFAR that proposed national monitoring and regional monitoring also of water level. So, and this system is obeyed using instantaneous observation. So, another limitation, another challenge that we have is the lack of data management to ensure quality control of hydrological information, and also the mechanism for data sharing. So in many countries, it's observation that we can find, so doesn't have the proper quality, inadequate quality control, and we are using this information into the system and also to conduct analysis. So and then we are running with a lot of bias in the results. So another big challenge so that we have are related with the lack the lack of continuous operation and maintenance of hydrological networks. So that are most of the case related with the lack of national budgets for operation. So and also we have we are confronted to issues related with the qualified personnel or staff knowledge to operate the networks. So as we can see, all these kind of challenges are producing effects to conduct an adequate water resources monitoring. So, however, let me talk right now about how WMO is supporting countries to address the challenge. Okay, basically WMO is providing support through programs of initiative to improve observation standards, to improve data sharing. So as part of WMO integrated global observing system called WIGOS, we have also a support through the WMO hydrological observing system called HOOS. Through HOOS, we are supporting countries in improved standardization of hydrological data and also to improve the mechanism for data share. So basically, the idea is that countries can be more operational to facilitate the access of data to different users and also for the different applications. So we are also supporting the countries in improving the knowledge of the hydrological status and outlook. So currently, the WMO is supporting countries through the Hydro SOS initiative called Global Hydrological Status and Outlook System. Through this support, we are working with several partners in the way to better reinforce capability of countries to conduct or to get information on the current status of water resources and also the outlook. So in the way that they can take better decisions on water management, on also information to support the different activities related with operational hydrology. So we are also supporting the countries in understanding and get better use of the spatial information. For instance, in the framework of a specific project, we have right now a project in Chad that is supported by the Cruise Initiative. So we are collaborating with the team to implement a hydrological monitoring system based on the estimation of water level by satellite altimetry. So basically, this project seeks to make better use of this spatial data for operational applications, for instance, to support decision making on flow warning and also to better conduct water resources planning. Finally, I would like to point out that this SMASH satellite constellation that is in perspective right now, so it's very promising. So it can contribute to address the challenge, and especially those related with the limitation of ground observation. And also, it can be very beneficial to provide information related with the current status of the rivers, lakes, etc. That is well aligned with our initiative, Hydro SOS. Thank you very much.
Thank you very much, Dr. Gasol. So we will take few questions that has been raised and maybe make it quite short. So the first question we have is from Johannes Budi from Indonesia, who has a question about is there any simulator that researchers can evaluate prior to the launch of SMASH mission? I think the idea is to follow on the idea that we had about the SWOT, which had a simulator where a lot of work was done pre-launch. And I think maybe Dr. Bianca Maria is a good person to answer it if you are still here.
Yes, I'm still here. So currently there is no SMASH simulator. I think the question that we are raising here might be solved at least by sampling maybe some model outputs every 24 hours at some satellite location, like JSON or any other that has a 10-day repeat period, and see if it could answer your needs. So at least to analyze the space and time sampling. And then, of course, you should be aware that there will be some error on the water elevation that is higher than from in situ measurements, for example.
I can answer very quickly the question from home, Abilea. I think we should do some effort in broadcasting information, technical information about the mission, like what frequency it's operating on, what's the bandwidth, what's going to be the performance, are there going to be geophysical corrections, and so on. And for that, we need to distribute some documentation to the audience.
I have a question.
Yeah, go ahead, Tanya.
So are you targeting some specific countries for the validation phase, the calibration phase? So what kind of specific areas are you going to be focused? Right now, we are in this moment talking about a constellation that is going to be launched. So, but for the adequation of algorithm, so what kind of specific region are you considering in this moment?
I can tell you something from the past. I've been involved in WICOS some time ago when I was doing River and Lake 25 years ago. And I think it's very important that we are able to do some validation in situ on the rivers that we're looking at, because of the geomorphology is different. And I can tell you, we had a hard time getting some collaboration with local people in Africa. They were more after finding 10 liters of gasoline to put in their Jeep to go and pick up data on the upstream of the river and things like that. So that then really be able to provide data just that they would have. And I'm very concerned that the validation on ungauged basin is going to be very difficult, exactly because, like you wrote in your slide, since 20 years, there's a decline in the data which is acquired in different regions of the world, which are probably the one needing the most the space data. And it's interesting to see why it's declining. Is it just because of lack of funding, or is it because, in fact, some of the data are not shared? And I think WICOS has been really pushing a lot to increase the data sharing, and especially for Transboundary River. And I can only encourage that this effort continues, especially that water is it's a common good for humanity, and not a commodity that you can exchange at Wall Street.
Yes, unfortunately, I couldn't show to my presentation, but it can be shared later on. Please, Anil, share with everyone the last version. So in which I chose some examples about some countries that are getting support to improve the data sharing mechanism through WHOS. So we are supporting countries also and improve the data sharing with global system through WIS, so based on WICOS standards. So and that is a part of WICOS standard also, but for hydrological data. So we have the La Plata authority basins in Latin America, and that is part of also of WHOS. We have the also Arctic regions that also are in this moment sharing data between them. So, and we have a specific countries. So right now we are working in the Caribbean, in Dominican Republic, and also in Africa. We are supporting Togo and other countries in improved data sharing. It's very necessary also for the validation phase, testing phase of these future products.
Tanya, thank you very much for this thoughts. I totally share it with you. I think it's very important. But for both for the CalVal, but also for the use, it should be clear which type of data from the constellation will be shared with whom. And on my part, I think both level 1 and level 2, so water elevation, but also satellite data, should be shared with the whole hydrology community, not just science, but also stakeholders, national and international agencies like WMO, both in non-real time, but also in near real time. So that's also, this question of data is also something very crucial that needs to be, I think, at some point clarified. What are the user needs and what could be provided?
I completely agree with what Sylvain said, and I think it's also dealing with one of the questions that we have received in the chat. Blaise Dawn is asking us whether this will be the case for Smash. It means will the data be available for free? Of course, it depends on the product level. As said by Sylvain, level 1 and level 2 are very likely to be available for free. But after a while, once you begin to talk about runoff, once you talk about more complex products, there is a cost. There is already a cost if you want to buy a satellite, to launch a satellite, and to operate a satellite. And this programmatic frame has not been envisioned yet. We don't know yet how to afford something like Smash, and the data policies that will be applied will very much depend on the programmatic framework that will be used in order to afford this mission. But what we can say now is that we will go as far as possible in a frame of free and available data, but that at a certain step concerning the complexity of products and their elaboration, we have to consider a price somehow. I don't know if it's clear to say that this way, but this is what I was meaning when I said we need a clear data policy and intellectual property according to the level of products. It has to be fair as possible with regard especially to the research community, which has been very much involved in the construction of all the algorithms that are applied to the data in order to get the best quality we can reach.
Angelica talked about the real-time access to the data. I think it's very important. If we want to really do something that helps, that has an impact on society and helps the people, like the people who are suffering from the flooding and in South Sudan example I showed, we need to have access in real time, just like meteorology, just like we have this near real time product which comes out in 3 hours. It's used into a forecast model through assimilation, and that is, I think, very important. And so the data policy should be focused on the forecast. And of course, if you want to do science like climatology and so on, have access to the data, maybe refine data a bit later, because that can wait.
That is a very good point, Jerome. So I cooperate, I have some exchange also with the developer team and also AgriMet, who is in this moment in charge of the FANFAR system, that is a real-time system for flow monitoring. So, and I understood that they try also to integrate the water level information into the modeling. So, but right now we have some limitation also with the availability of this data. So I guess that later on, when you have this network deployed, so it can be very interesting in try the water level products into this type of system. I would like to know if you have any perspective about when this network is going to be operational.
I think this mission can be launched as soon as it can be built, but it really depends on the funding sources to get this out of beyond the investment done by CNEF to get into phase A, to go forward to the development phase.
Yes, this is more or less what I said just before, Jérôme. It will principally depend on the programmatic frame that will be used in order to the financial support to buy the satellite constellation and the ground system that will process this information. And for sure, once again, the best effort will be done in order to give the data at least at L2 level. But once again, a clear data policy has to be constructed so that we can ensure a fair positioning of the for the researchers. Once again, nothing of all the stuff we've been discussing since the beginning of this afternoon, nothing of all that would have been possible without a very strong involvement of scientists, of researchers, of engineers that come from the public side of the story, that want to and that have given all their skills, all their knowledge in order to elaborate this data. But this data is not realized. All this system is not realized for free. It has a cost. It has the cost for people who pay taxes at French European level, and the free, once again, the free and open access, which is very trendy today, initiated principally by America, by the United States. This free and open access politics strategy has to be considered very, very seriously and critically, since on European side we don't have the same infrastructure, the same level of development of infrastructure, the same as Northern America has, and providing all our data for free, regardless, not only altimetry, but all the data that are in relationship with hydrology or any other subject. This data policy has to have to be very attentively, very carefully thought before any dogma application. So if I want to summarize, I would say we do our best to provide the data for free, at least at level 2 product. The science committee will have the priority to this data, and then any more developed product with more added value, it will have to be discussed. It cannot be given this way without having a serious strategy for data policies and intellectual properties. I hope what I say doesn't sound too restrictive. It's just a question of being fair with regard to countries who pay the satellites, with regard to countries who process the satellites. The infrastructure has a cost, and this cost, these infrastructures have to be sustainable. We always talk about sustainable goals development. I do believe that in the sustainable goal development, we should take infrastructure into account.
Yeah, Philippe, it makes sense. Like everything, at some point, you can create a market with free data. The GPS signals is free, and look how much cash is generated by GPS receivers and mapping application that we have in our phone. When you acquire the data, when you have launched the mission, you have run the ground segment, then you end up with a lot of downstream activities to transform data into information for stakeholders who are ready to pay, because getting this information usually mitigates another big toll. I was looking for the word, a big toll when there is flooding and drought that you can eventually anticipate by having a good prediction. And so, there is a business model that has to be invented for everything, because everything has a cost. There are salaries to be paid, and at some point there is also the consideration that it is the role of let's say the funding agency through governments to protect the people from hazards. And so
Sure.
beyond the market that you can develop downstream with some data that you put for free, let's say, and open, then you also have to do something to protect your population and tell them early enough to go to the first floor, because a flash flood is coming.
Yes, of course. We all want to make possible the development of risk management services and go as far as possible. We all agree with that. It's just to say that I just wanted to say that there is a place. It's consistent with market. Market doesn't no rules. We can think of rules that will be applied, and there are rules that are already currently being applied concerning services for civil security. And there is no doubt that all the information we talk about will be used as much as possible in this kind of services. But on the other side, if we talk about business that can be made with this information, I think it's also consistent with thinking of slightly modified rules compared to the basic one, which is the free and open access, which is doesn't really make possible any kind of. But it has to be. There is a need for a roadmap. There is a need for a very serious studies concerning all that. It's a very tough question. We will probably not find the answer today, but it was just to mention that the question of rules, the question of policies is not as obvious as it is usually mentioned.
Well, it's obvious if there's a big funding body that takes care of everything, using the taxpayers' money and then distributing the data for free. This is what we do in the Copernicus program. In this case, the idea is to find the right funding sources. There may be multiple, public, private, partnership, and so on. I would like to say that I think one action is to promote a little bit SMASH, because if you ask Google, Google doesn't know much about SMASH, which is not very good. There's a nice paper that was published in 2019 and by Jacques Véron about Altica, showing that there's a lot of things we could do with this concept and to build a SMASH. There is an EGU paper that Denis Blumstein presented in 2019. But if people in the audience look for some information, it's not obvious. All this information, I think, has to be given to everyone very rapidly. And this effort that was done like today, I think it's a very good point. And I think every, 6 months or something. And I think an important milestone is the Hydrospace 2023 in November, where we can discuss more in detail and maybe show more about the SMASH concept that Denis Blumstein worked on for so long. Okay, so in the name of everyone and no one, I would like to say thank you to everyone, and there we go. Bye bye, everybody.